Okay, we're going to follow up the lecture on sampling and talk a little bit about how or what properties of a sample make it so we can have a more accurate inference about the population parameter. And there's two things that really matter in your sample if you want to make an accurate inference to a population. One is the sample size. The larger sample you take, the more elements of the population you'll have, and therefore you should be able to make a more accurate inference. And then the one that's actually more important property here is that you take what's called a probability sample. A probability sample is a sampling technique where the sample is gathered in a process that gives all the individuals or units in the population an equal chance of being selected. It doesn't mean that all units and individuals within the population are selected. It just means they all have an equal chance of being selected. Now, sometimes researchers will take non-probability samples, and those are just samples in which the sampling process, means that some individuals or units in the population are going to have a greater chance of being selected than other units. And those usually results in biased estimates or biased inferences, inaccurate inferences. So what we want in order to be able to take a sample and make an inference to a population is you want to have a good sampling technique, which means a probability sample. And there are a range of different types of probability samples: a simple random sample, cluster sampling, stratified sampling. But they all have this one element in common, that each unit or individual in the population has an equal chance of being selected. And that's the actual more important feature of a sample that's going to allow us to make an inference to the population. Sample size matters, but only to some extent. So let's go ahead and do what we did last time, which was define a population, which is the sequence of numbers from 1 to 100. We know the mean of this population is 50.5. And then what I'm going to do is I'm going to take a non-random sample. I'm going to take a non-probability sample. So I'm going to define this object NPS for non-probability sample, and it's going to be the sequence of numbers between 1 through 40, right? And so we're only sampling from this range of these first two rows of the population. And what it means is any elements from rows 3, 4, and 5 here do not have a chance of being selected in our sample, right? I've purposefully excluded them from the sample. So we're probably going to get an inaccurate estimate of the mean. But what I also want you to see here is that I've taken a large sample. I'm taking 40, right? And I could even add this up to 50, right? I mean, I might as well just go ahead and add 41. Oh, whoops, let's go ahead and do this, right? Let's just go ahead and take half the population here, just to show you that size doesn't really matter if you use a non-probability sample. Right? So here we have this object NPS, and it's the elements 1 through 50. Now let's take the mean of NPS, and as you would guess, it's 25.5. So we're way off the population mean, right? Even though we took 50 out of 100, right, our sample is basically half of the population, we're still getting a mean estimate of the population parameter that's very inaccurate, right? So that's what we mean by the type of sampling you do, the process. Having a probability sample is much more important than the size of your actual sample. Okay, so let's go and use R's built-in random sampling generator. So this takes a random probability sample, this command here, sample, and we're going to take it from the population, and we're only going to sample 5 units, right? So a very small sample here. And we calculate the mean of that sample. And so the numbers that it drew randomly were 45, 1, 46, 44, and 53. And we get an estimate of the mean that's 37.8. Now, even though we only had 5 units in our sample instead of 50, we got a population estimate that was much closer to the real true value of 50.5, right? It's not exact because we only took 5. We took a very small sample, but we got something that's much closer, right? And so with the central limit theorem, let's do another one real quick. So here we take a different sample. We have 89, 13, 31, 76, 50. It's a probability sample. It's a random sample. And here we get a mean estimate of 51.8, which is really close to the population mean with a very small sample. So here you can really see that you can see two things. One, that sampling actually works sometimes. Sometimes you get really close to the mean. Other times you'll be off. a little bit, but then you'll also see that a small sample can get you a more accurate depiction of the population, even though you're sampling only a few elements from the population. Let's do this a couple more times and draw different random samples and calculate the mean. Here the mean was 50.2, so again, very close. Here it was 41.8, so undershoots it, and then 60.2 for the fifth sample, 5 units, and that's overshoots it. And what the central limit theorem tells us here is that as we keep on sampling, right, in this create a sampling distribution, we're going to get something that's closer to the mean. So if we average those means up, we're going to get an estimate of the population mean of 48.36. Right? So then let's do the exact same thing. Take 5 different random samples with replacement, and this time from the population, and this time we're going to increase the sample size to 10. So we increase the sample size to 10. We take a sample that has 10 units, 48, 9, 46, 66, 20, and so on. And let's calculate the mean. And here we get a mean of 40, right? So it doesn't really improve. We don't really see a big improvement based on one sample from sampling 5 to 10, right? Let's do it again. One more. 41.3, again, we undershoot it. And let's just go ahead and take the rest of these 5 samples here. Let's average up those sample means, and we get 49.54. So we're really close to the population mean of 50.5 from only taking random samples, probability samples of 10 elements out of those 100. And we don't really see much of an improvement, if any, when we sample 10 instead of 5, right? So what this should show you is that the type of sampling matters. It's much more important than the actual numbers from the population that you sample. Increasing your sample size will get you more accuracy, particularly in the long run, but what really matters is the type of sample you take.